In the previous lecture, we described the detailed steps of form and what sort of output we might get from a first order reliability analysis of an element. So let's recap the steps. First, we map X, the space of basic variables, onto U, the space of independent standard normal variables, and hence we map the limit state function G from X to U and obtain the new limit state function H. And then we find the minimum distance to the line H equals 0 from the origin, and that point is called the checking point, the optimal point. The distance is called beta very commonly, and it's also known as a reliability index, and the failure probability of the element in question is approximately equal to phi of minus beta, where phi is the normal CDF. We discussed why we have to include the signum function to be more complete. So pictorially speaking, this is what happens. On the left, you see the space of basic variables x1 and x2, and the joint density function of x1 and x2 is indicated by those PDF contours. You also see in blue the limit state line, which is a hypersurface in n dimensions, and clearly you see the safe and fail domains demarcated by the limit state. And when we map from X to U, we get a new limit state, which is H, and the PDF contours are now concentric circles around the origin because it's the independent standard normal space, and there we find the minimum distance and the minimum distance point, which is U star, as you see, and the distance is beta. So obviously the map, we spent a good amount of time discussing the kind of maps we could use from going from X to U. We mentioned the second moment transformation, also known as the Haushofer-Lind transform. We discussed the full distribution transform. We discussed the Native transform. We discussed the Rockwitz-Fiesler transform and the full distribution and the Rosenblatt transform. So now to summarize, the key steps is that map, as I mentioned, and then to find the minimum distance. Now, points to note is that H is not required to be in closed form, so we don't need really a function, but if we have a way to estimate it pointwise, that would be quite good. Gradients are not essential, although the methods that we described are based on gradient projection methods, so gradients are very useful to have if possible. If not available analytically, it can be estimated numerically, but that slows down the computation. There are many optimization schemes other than gradient-based methods, but one point to note, which can be significant, is that after all, this is a nonlinear optimization problem. So the global optimum is not guaranteed. So we have to keep that in mind. With that in mind, now let us solve a set of problems with FORM and with increasing level of complexity.